Hello, this video is on the very basics of Portland cement concrete. Portland cement concrete has three main components. They are cement, aggregate, both coarse and fine aggregate, and water. When you want to think of coarse aggregate, you want to think of stone. Fine aggregate is generally sand. Sometimes it is crushed stone. But it all really depends on the scale of the thing you're going to make out of concrete. So the most important ingredient, the thing that makes everything work, is Portland cement. Portland cement is highly engineered, I would say, by chemists, and it has four main compounds. There's tricalcium silicate, dicalcium silicate, tricalcium aluminate, and tetracalcium aluminoferrite. The cement is mostly tricalcium silicate and dicalcium silicate. Tricalcium aluminate and tetracalcium aluminoferrite make up a smaller percentage of the Portland cement. Now, the important thing for you to remember is that concrete does not dry. Concrete cures. Drying is the removal of water. Curing is a chemical reaction. So, Portland cement is formulated to fuel this hydration reaction and make it as efficient as possible. So, generally what happens is one of the four compounds that we discussed before, tricalcium silicate, dicalcium silicate, tricalcium aluminate, and tetracalcium aluminoferrite react with water. So they join with water, and that's why it's a hydration reaction. So the hydration reaction consumes the water. The concrete does not dry. The water does not go away. Some evaporation does occur, but that is not what hardens and gives concrete its strength. So generally what happens is that if we look at the original compound, gets added to water, and it creates hydrates and another compound sometimes. What we've designed the hydration reaction of Portland cement to do is to create the hydrates. The hydrates are what give the concrete its strength. The other compounds, like if we look at tricalcium silicate and we add 6H2O to it, we end up with calcium silicate hydrates and calcium hydroxide. Calcium hydroxide doesn't give the concrete any strength, but if you combine that with if you combine the water and the calcium hydroxide with tricalcium aluminate, you'll find that creates calcium aluminate hydrate. So what Portland cement concrete has been engineered to do is to create hydrates. And it can take the products of certain chemical reactions and use those products to create more hydrates. The whole goal in the end of this is once you've hydrated once you've cured the concrete to its maximum amount, all that's left of the Portland cement is hydrates. Now, here is how the curing process works. Let's say we have just a box. Inside that box, we're going to have, we'll use green for cement because I like green. We'll have Portland cement and we'll have some water. Now, what happens is the Portland cement and the water begin to combine at the interface. This makes the water highly alkaline. or basic. Now, obviously, you're probably more familiar with an acid than a base, but both of them are very bad for you. So when you're mixing concrete, it's generally not good for your skin to stick your hand into it. It won't melt your hand off, but it's not good for your skin. It'll dry you out, and no one likes that. So when you're handling concrete, it's generally good to wear gloves. But when you first mix the things together, you'll have cement, you'll have water, and they'll start to combine, making the water very alkaline. This process will continue, and as it continues, space will start to form between the cement particles. So instead of having one big blob of Portland cement, we have smaller globs of Portland cement surrounded by water. Blue is water. And these particles will be melting down, making the mixture more and more alkaline. So we'll still have that interface where they are breaking down, and each one of these will be breaking down. Of all these things, the aluminates hydrate first. And the amount of aluminates kind of dictate what your initial set time and strength are. Or initial strength, not final strength. Well, it all goes into the final strength. This gives you your initial strength. Now, with these particles separated, they begin to hydrate, and the hydrates form. And what the hydrates form, we'll have to remember that there's water everywhere, is that the hydrates start forming a weak skeleton. So there'll be hydrates forming between these particles, and they create a weak skeleton, which gives you your initial set. And this initial set happens somewhere between 30 and 90 minutes of pouring the concrete. Following the initial set, the C, S, and H phases begin to form a rigid structure. This gives you final set. And while we have reached final set, we still have cement particles we still have the structure from initial set. But now we're starting to get more and more different hydrates forming a structure between all the things. Now, all these X's I'm putting in here, these X's are the skeleton that holds everything together. The X's are good. The more X's we have that overlay, the stronger our concrete will be. While all these more X's form, the particle sizes of the cement shrink and shrink and shrink. At this point, we have final set, and you can't do anything with the concrete really, and this happens between 10 to 24 hours of having poured the concrete. Now, hardening is a phase, but it's a phase that will continue for the rest of the concrete's life. Basically, concrete will harden until there is no Portland cement left. So if we ever get to the phase where we have no Portland cement left, all we're going to have is hydrates, and this will be the strongest structure we can possibly have, because we've gotten rid of all the Portland cement and all we have is hydrates or structure. And this structure will be holding together all the aggregates and sand. Now, hardening continues as long as there are cement particles in water. So basically, you could make something out of concrete. Some water could evaporate, and every time it rains, it gets wet, and it will continue hardening the concrete until there is no cement left. The full strength for concrete is considered to happen at 28 days, and generally at 7 days, a mix is at 70% of the 28-day strength. So if we look at a curve of how strength occurs in concrete, if this is days and this is strength, we get rapid increase and then it levels off over time, almost staying the same. So at 7 days, we're at 70%. At 28 days, we're considered 100%. And then it will continue curing or hardening until there is no Portland cement particles left. Now, curing is controlled by the type of cement you use initially. There are 5 types of cement. There is normal cement, or type 1. There's type 2 cement, which has moderate sulfate resistance. Type 3 cement, which has high early strength. Type 4 cement, which is low heat of hydration. And type 5 cement, which is high sulfite resistance. By far, the 2 most common cements are type 1, normal cement, and type 3, high early strength cement. Type 1 is probably the most common because it is the cheapest. Type 3 is high early strength, which does exactly what you think it was. It gives you higher early strength. So basically, if I want my concrete to have strength faster than normal cement, I get high early strength. Type 2 and type 5 give you resistance to sulfate, which would generally eat up concrete. So type 2 and type 5 you use when you're putting concrete in an aggressive environment. Type 5 is probably used more than type 2 because you just obviously get higher sulfite resistance. So if we're going to deal with it, you're going to use the high sulfite resistance. Type 4 concrete is very interesting. This is low heat of hydration cement. So low heat of hydration, well, first off, the hydration reaction is an exothermic reaction, which is really interesting. So when concrete cures, it actually gives off heat. Now, the concrete curing process can generally only happen between over a certain set of temperature, being if it's too cold, you won't get hydration. If it's too hot, you won't get hydration. So when you're doing a massive pour, something like the Hoover Dam or something like that, with all that concrete curing in the same place, the heat can actually get too great and damage the hydration process. So when you're doing massive concrete pours, you're going to use a low heat of hydration cement. So these are for like giant things made out of concrete. But what's really interesting is if you make concrete, it starts curing, you put your hand to it, you can actually feel the heat coming off of the concrete. Now, the key to everything is the water-cement ratio. The lower the water-cement ratio, the better. The ideal amount of water in terms of strength and durability, neglecting the effects of aggregate, would be the exact amount of water to completely hydrate the cement. Now, this is not possible because this concrete would be unworkable. What makes concrete flow like a liquid is the water we add to it. So one reason concrete is the most abundant thing on earth is that you can place it like a liquid and it hardens into a solid that's very strong, especially in compression. So if you don't have enough water in there to make it flow, it's very hard to use and it's very hard to get anything of quality made. So we need to have excess water to make the concrete workable. Now, what does this mean? So, we have our concrete, or our window into the microscopic concrete, and we have water droplets. The problem with these excess water droplets is that the hydrate structure cannot grow through these excess water droplets. So what these water droplets end up being are large voids in our final concrete, which interrupt the hydrate skeleton. This ultimately weakens our concrete. So the real thing that's important in concrete is knowing how much water we're putting in the mix, because we want to be able to control our strength. Formal concrete design is basically filling a known volume with known materials and reducing the amount of water voids. So it's filling that volume and knowing how much water is actually in the volume. So in terms of aggregates, coarse aggregates are the backbone of concrete. The strength of the concrete, they give the concrete its maximum strength. So a concrete mix can never be stronger than the aggregates that you put in it. Fine aggregate is used to fill the voids between the coarse aggregates. It basically takes up volume. It's like having basketballs and filling the room in between them with ping pong balls. Now, the properties that are important for our aggregates: for the coarse aggregate, it's the bulk dry specific gravity, the bulk saturated surface dry specific gravity, and the absorption. For the fine aggregates, it's the bulk dry specific gravity, the bulk saturated surface dry specific gravity, the absorption, and the fineness modulus. Now, in here, I've said saturated surface dry twice. So let us just start with a generic aggregate. These are natural things, and we'll put one cut in it, and we'll put some internal holes in it. All right. So this aggregate is bone dry. In this state, what will happen is if we introduce water to this aggregate, it will start filling the voids. And there are multiple states. So inside here, we have some voids that are completely cut off from the outside. They're just empty voids. Nothing can really get in or out of them without a long time to absorb. Here, though, we have an external void. So if we introduce water to this particle, it'll absorb up some of that water and fill up this void here. If we only have a little bit of water in there, we call this aggregate partially saturated. Okay? If we add a partially saturated aggregate to a concrete mix, what it will do will draw mixed water out of the mix and hold it in itself, so that it will take water away from our hydration reaction. So if we add dry aggregate or partially saturated aggregate to a mix, it sucks water out of the mix. If the aggregate is at the perfect condition, where its voids are completely filled, we call this the saturated surface dry condition. If aggregate is added at the saturated surface dry condition, it will neither bring water to the mix or draw water out of the mix. If we add fully or oversaturated aggregate to the mix, being that all the voids are filled and it's surrounded by water, when we add this aggregate to a mix, it will bring water to the mix. So if we add this, we'll be adding water to our mix unintentionally, and we'll have to reduce the amount of mixing water. So when we do our concrete design, we consider the aggregates to be in the saturated surface dry condition, meaning that all their voids are filled with water and it's not going to pull water out of the mix, and it's not oversaturated, so it's not going to add water to the mix. At the end of a mix design, we go back and account for how much water the aggregate has to adjust the mixing water. But mix design is a game of tracking water. If our aggregate's going to take water out of the mix, we need to know. If the aggregates are going to bring water to the mix, we also need to know. Now, I said there are three main ingredients to concrete: aggregate, cement, and water. But modern concrete is kind of a wonder because we have so many different admixtures and chemicals that we can do all kinds of different things with concrete. Things we thought weren't imaginable. Some general classes of admixtures are water reducers, superplasticizers, air entrainers, retarders, accelerators. We can add all kinds of supplementary cementitious material: fly ash, slag cement, silica fume. We can get our concrete to do lots of amazing things. Water reducers, they obviously reduce the amount of water you need to have a concrete mix. They let you have workable concrete while reducing your water to cement ratio. Superplasticizers allow your concrete to be super flowable. Air entrainers put small bubbles into your concrete. Now, these small bubbles interrupt the skeleton just like water voids, but they're much smaller than water voids. And what they allow for is when water gets in your concrete and it freezes. Water is a very interesting substance in that when it goes from its liquid to its solid phase, it actually expands. So when water gets into your concrete and freezes and expands, instead of cracking your concrete, it will fill into these air bubbles. And when it freezes, it stops it from damaging your concrete. So air entraining your concrete, while reducing the strength a little bit, adds durability to it. Retarders slow down the hydration process. So if you have to send a ready mix truck over a long distance, you add retarders to the mix, drive it to the site. Once it gets to the site, you can add an accelerator to speed up the curing process. So you can have concrete travel over a long distance. Supplementary cementitious materials give your concretes different properties. They're also generally recycled material. So fly ash is a product made from burning coal. Slag cement is from casting concrete. We generally consider these recycled products that we can use in our concrete, that we have a lot sitting around, and we can use them to make concrete, so we don't have them sitting around as much. Now, mix design, and when I say design, I use it in a loose term. It's not design in that we know the properties. The design is we have a guess. The only way to truly know the properties of a concrete mix is to make it and test it. So mix design is essentially a guess. It is a highly empirical process, meaning that our current mix design is based on the things we learned from doing mix design. The strength and properties of a mix need to be understood statistically because we're using natural aggregates or natural products. There's natural variability. The only way to understand how a concrete mix is going to behave is to make it and test it so we understand the behavior. And once we have enough tests, we can understand how it works statistically. Now, in order to make certain that the concrete is strong enough, we need to know the standard deviation. So I'm going to draw some statistical axes here. And on it, I'm going to draw a bell curve because the strength of concrete is a normal distribution. Now, we do cylinder break strengths to understand what the strength of the concrete is. Now, drawing a line down the middle, and the middle of the normal distribution is the average. This gives us the property F prime CR, which is the critical strength. Now, if we used F prime CR as our design value for the strength, we wouldn't be very good designers. Because since this is the average of a normal distribution, if we use this as the design strength, there'd be a 50% chance that our strength is greater, and there's also a 50% chance that our strength is less. So what we do, knowing that the concrete strength is generally, well, not generally, has been shown to be normally distributed, we look at a value that is 1.34 S, which is the standard deviation, which gives us the 10th percentile value. Meaning that when we use this as our design value, there's a 90% chance that our concrete strength is higher, and there's a 10% chance that it is less. This value is what we call F prime C. So when you do all your reinforced concrete design, you use ACI 318, everything is based on F prime C. F prime C is not the average strength of a concrete mix, it is the 10th percentile value. Now, in order to have a large enough sample to determine what F prime C is, you need basically 30 strength tests. If you do not have 30 strength tests, there are modification factors you can use. So, for example, if you have 15 tests, your modification factor is 1.16, meaning that if you have an average strength you're going to basically do 1.13 S and then reduce it by 0.16 until you get to the 30 samples when you can use the 1.34 S, meaning that you get that 10% value from your standard deviation. Now, generally, you're not sitting at a place where you have less than 30 tests. If you, as a student or as an engineer, are say, do a design mix, you're probably doing a design mix from scratch. When you're doing the design mix from scratch, there are simple adjustments that you do to your mix design. So let's say you're going to say, I need an F prime C of 4,000, and I need to get an F prime C of 4,000, which would be 1.34, the standard deviation, minus the average value. You're not going to get that. But you're going to say, all right, I need a 4,000 PSI concrete mix. So instead of actually designing a 4,000 PSI concrete mix, I'm going to add 1,200 PSI. So now you do your 4,000 PSI mix plus your 12,000 PSI, and you're going to just design for 5,200 PSI. Now, you're going to go through your whole mix design for 52,000 PSI, and you can generally say this is a 4,000 PSI concrete mix. Now, if this is how we design it, let's do a thought experiment in the reverse. You're on a site and you're pouring a concrete beam and you're sampling your cylinders and you're breaking your cylinders. So you're going to sample your cylinders. At 28 days, you're going to break them. And most likely, you're going to say, well, I'm looking for 4,000 PSI. When you break all your cylinders, most likely what you're going to end up with is 5,200 PSI. So if you're an engineer and you ordered a 4,000 psi concrete mix and you start testing and you get 4,000 psi at your brakes, this needs to be a red flag in your mind, because if we zoom back, your design strength of 4,000 psi is F prime C. If you break a number of cylinders and this turns out to be your average, there's something wrong, right? So there, and I'm going to go back to this slide so that I can burn into your mind, is that mix design is highly empirical. The only way to know a concrete strength is to test it, and when we use it in design, we need to first look at the statistics of it before we can just use it. Maybe this be your first lesson that statistics is very important to your daily life.